and we're back for the final session of today. Yeah, now we're going to the very other corner of the world. It's on the West Coast. We welcome Florian Kolb from Intertrust with us. So Florian is an industry veteran with more than 20 years of experience in the energy industry. And he will talk about how Intertrust is using IoT and minimizing the time to AI. Engage.
Okay, excellent. Yeah, so good morning or good evening, everyone, depending where you are. So as Clemens already said, my name is Florian. I work for a San Francisco-based technology company called Intertrust. We are busy with data interoperability and digital rights management. And of course, there's a strong angle to AI. And also myself, I've spent 15 years in the European energy industry. So the title of my presentation is how to reduce the time to AI to accelerate the energy transition. And when I was thinking, where to start, I think we have to start with the climate. It all starts with our climate. So as you are aware, we have this thing going on called the energy transition, which is necessary to meet our 2050 climate goals to limit the global warming by maximum 2% and also reduce the CO2 emissions. And if you analyze all the studies, publications around this topic, then there's a clear call for action to accelerate this energy transition. And the decarbonization, the power sector, the electricity sector is really the starting point because it's one of the biggest emittents, and also the world is going electric. And the plan actually is that based on clean electrical energy, we would also decarbonize the mobility sector, so transportation, cars, and so on, as well as the heating and cooling sector over time. And we call that in the energy industry sector coupling. So we have like these three sectors which operate independently today, which will be combined over time via green electrons. So that's the idea. And you can already imagine that this is a big coordination problem that's coming up. As I said, the world is going electric. The electrification of everything is expected. And so the share of the global energy demand met by electricity is projected to grow by around 60% until 2050. And clean electrical energy will enable green hydrogen. That's also very important. So there are sectors which are very hard to turn electric or turn green. And there is a strong belief that green hydrogen will be the facilitator for that. So, for example, in heavy-duty transportation, shipping, airplanes, and some energy-intense industry like the chemical industry. So the world is going electric. What does that actually mean? There are some very big, hairy problems waiting on the other side if we want to achieve that, turning everything into electric and also green electricity. And one of the big challenges where also AI comes in is that energy is a real-time system with a lot of complexity. So just a few things to mention. We have an increasing share of intermittent renewables. So they produce energy when the sun is shining and when the wind is blowing, and that's not like constant over time. We have a strong increase of decentral energy assets, such as smaller and larger batteries that are being used to stabilize the system. We have new roles for distribution grids, so they have to connect these decentral energy asset storage or also production. And we now have a two-way traffic of electrons going back and forth. So coming from the edge, going to a more central place and the other way around. We are moving from central to more decentral power dispatch. We have the sector coupling phenomenon that I already described. We have a very complex financial transaction system around energy. So energy electrons are being traded, and that creates additional complexity from a financial perspective. And also the cost for energy production, but also transport, are a key economic and political factor. I don't think I have to make any comments about what's going on in the world right now, which exemplifies that greatly. So this is the big and hairy problem. So I can't go through that in detail, but this is actually how the energy world of the future will look like, with sectors, with massive increase of renewables, and just a lot of complexities. And these complexities are the key drivers for AI in energy. So the future energy system is impossible to manage with the traditional capabilities and approaches that we have. A central system which is regulated, which has regulated processes that are also described in software and in IT. That's not going to work anymore. We have a real-time data issue here. So the system generates a lot of real-time data. We need advanced analytics to crunch and analyze the data, and we need a high level of automation. The speed and also the cost of the transformation is very important. So we need to increase the speed, and we need to lower the cost, and we need to connect the system that is very distributed and very complex. And that's actually where digital or digitization comes in, and also AI, because these are things that digital and AI can do very well with relatively low marginal cost increases when the challenges increase. We also need more predictions and more forecasts of energy supply, energy demand, and so on. And we also need automated decision-making, which are drivers for AI, and what actually is something that AI can deliver. So I will make a small overview of the use case examples, just to give people an idea, where can we apply AI, and for those of you who have a startup or are in the business should focus or could focus on. So actually AI can add value across the entire electrical value chain in many, many use case areas. So we start at the left with renewable generation. If you think about solar and wind and onshore wind and offshore wind is maybe a good example because it's a very complex, large-scale operation. And you can imagine that already in the planning and in the construction phase, there are a lot of things to consider, where historical data that can be analyzed with AI can give a lot of hints how to approach planning, how to approach construction, how to organize an offshore wind farm with regard to the position of the different turbines, and so on and so forth. So there's a lot of weather modeling. There's a lot of technical modeling that can be done where AI can support. That should lead to an optimization of the assets, and with regard to design, with regard to failures, with regard to outages, and with regard to maintenance. To give you an idea, of the overall production cost of an offshore wind farm, around 20% of the cost goes into maintenance. So every smaller optimization on the maintenance cost side can help to make the asset more valuable. On the power dispatch side, we need AI-supported supply and demand forecasting to minimize the curtailment of the assets and actually maximize the power output, because we desperately need the green electrons. Also, in the integration into power grids, AI can play a role. And of course, to link renewable generation with the hydrogen economy. So green hydrogen works as follows. We take electrons from wind and solar, we turn them into green hydrogen, which we then store or transport and then use. So there needs to be a link to the green hydrogen systems. And also the idea is to use excess electrons from wind and solar to generate green hydrogen. And that's all a big coordination and calibration exercise. So on the grid side, many, many use cases. At the end, I think what we have to try to achieve is to enhance the capacity of the existing transportation and distribution systems and grids, and extend the lifetime of the existing assets. Because if we look at the studies, what they indicate, to get to a a level of green energy and green electricity in 2050 that's required to meet the climate goals. We have trillions of dollars of investment required in grids. So it's a huge chunk of money that needs to be invested. And there will be a capital shortage problem. So we need to figure out where to put the money so that it creates the most value for economy, society, and so on. In grid design and planning, we can use AI in grid performance management. Also, we have one phenomenon that's interesting in the low voltage grid, especially. We have significant information gaps because these downstream assets are not fully equipped with sensors at the moment. There are initiatives to do that, but that also costs money. So we think that also AI can help us here to model grid phenomenons that are based on models and not based on actual data. Also, data access is a very important topic in this area because often the data is there, but it's restricted by privacy law or competition law, GDPR, for example, on the privacy side. Think about smart meter data, energy consumption data, and so on, which is not so easy to share or process because it has some privacy implications. Electric vehicles is a next area where we have a huge upcoming new consumer of electricity. An electric car, in average, needs 3 to 4x the electricity that the normal household consumes during the day, assuming a standard commute. So, but it's also a source for energy. So when you come home, plug in your car, the question is, what's going to happen? Who is steering the charging? At the moment, the way it works is you program on your Tesla, for example, that the charging should start at midnight or at 10 o'clock. And in the future, this will be an automated process where actually AI will decide when to provide services to the grid that are needed for balancing, still ensuring that you can use the car in the way that is needed. And the last area, which is also a very juicy one from an AI perspective, is demand side flexibility. So how do we forecast when we have which demand events? How do we create flexibility around all the energy consumers that are behind the meter? In industrial areas, that's already common, but for example, not in the B2C area. So fridges, electric vehicles, washing machines, and so on, theoretically can all provide services to the grid. So energy, power quality, or the provisioning on power when the grid is short in power. So how do we steer that so to aggregate and manipulate energy demand? And AI can play a major role here in the future. Also, one word that we hear often are VPP, virtual power plants. So this is actually the virtual aggregation of load that's collected and then provided as a grid service when needed. Also, this is a very data-rich area where AI can fundamentally support the energy transition. So if we think about AI, we have to think about which data types and data sources really enable AI. And what we can see here, the message is that there is a lot of data which needs to be considered. So it starts with environmental data, wind, sun, clouds, major environmental events, flooding, storms from the past that have to be analyzed, temperature, marine data, especially for the offshore wind side. So that's where where it all starts in renewables. Then we have supply and demand data, power generation forecasting, production assets, availability, condition of the assets, micro flexibility data, so the EVs and the home thermostats and the fridges and so on. Financial data plays an essential role. So at the end, things work when people can monetize their assets. So we need to have very accurate power price predictions. We need to understand what are the marginal costs of the energy production, benchmarking data, so a very rich financial data universe. Then we have hardware and sensor data coming from assets. So SCADA data, other OT data, IT data that's kind of floating around in systems already. Relatively new categories are images and videos. So people are using drones these days to collect data around renewable assets or grid assets to detect anomalies, or one of my favorite ones is the woodpecker hole in wooden poles. So that can be detected with a drone, and with AI these days. Also grid assets is AI is used for inspection purposes. And then last but not least, we have existing IT and data systems. So most of the energy companies are pretty big organizations with ERP systems, with workforce management systems, with regulatory reporting on carbon footprint, carbon accounting, and other reporting requirements. So there is a lot of data that can be used. So here's the problem. If you look at today's IT landscapes, they consist of a lot of distributed devices, of cloud infrastructure, disparate database systems. And so we have certain data availability issues. We have data standardization issues. We have issues to access the data, to make the data interoperable. There are security concerns around data breaches. There are concerns around system integration. So how do we bring the data together so that AI can unfold its full potential? And of course, we have to safeguard governance and compliance, like data privacy laws, issues that are very important, especially in energy, because we are talking about an industry that runs a mission-critical asset. So the goal actually is to get rid of all of these problems. So what we actually want to achieve is full data interoperability, regardless of the type of the data and where the data resides, and that the sharing between disparate multi-party systems like a decentralized energy system is being increased, and so is the availability and the quality of data to enable AI applications that can then provide the benefit to the energy transition, so speeding it up and making it more affordable. So that's where we want to go. And now the question is, of course, how do we achieve that? And so what actually we propose, or what we have developed, is a virtual layer of distributed data and devices that's bringing AI and data together. So this is an abstraction layer that we see coming more and more, that is able to source data from wherever the source is. So be it in cloud systems of the different providers that are listed here, or whether the data is hanging out in an own on-prem data center, or in a third-party data center, or in ERP systems, or in modern data warehouses, or in other database systems. So it shouldn't really matter where the data resides and where the data come from, and also whether this is data from one company or from multiple companies. One of the phenomenons of the energy value chain is that it's very fragmented, and we have many, many different players that are active in the various value chain segments. And because the system is developing the way it's developing, we need more interoperability between these players, and we have to break up the silos. One of the very prominent silos is the retailing of energy and the grid. Because of regulation, there has to be a Chinese wall between the customer side of the business and the grid business, because grids are natural monopolies, and they have to treat any retailer of energy at arm's length and in the same way. So there can only be a limited information exchange. On the pure electron side, that's an issue, because the demand gets more volatile from day to day, and the grid has to know that. So we have to find ways to let people talk to each other, that it's competitive, friendly, and doesn't create problems with antitrust. So we have this internal data operability that we need for AI, but also between different companies or organizational boundaries. And then, of course, we have to ensure that, especially if it's like, for example, device data, that nobody has tampered with the devices and the data is really the data and the device is really the device. If that's not secure, then the risk of blackouts and brownouts is being increased. So how does this work? There are like very powerful big data features available in these days. So one is data virtualization, where we define logical data sets from a variety of data sources, including relational databases, data warehouses, or data lakes that reside on-prem or in the cloud. Governance is important. So who can access the data, under which conditions, which has to be automated to access data that is located in multiple databases, object stores, or file systems from a single point of control, which is important to enforce the governance, and also to be able to impose row and column-based restrictions that allow policies to be tailored to the needs of the data consumer and the AI. And then a third element, which is important here, is secure execution. So we have to deploy algorithms, workloads, and services in isolated execution environments with dedicated memory and compute. What does that mean? Data can meet AI without exposing the data to the AI owner or exposing the AI to the data owner. So to create like trusted execution environments in energy will be very important, because we can not always have like lengthy processes between multiple parties to agree on how to secure data, if there is a technical solution to provide a secure exchange and enable AI access to the data. So some of the technical experts, and then I will wrap up briefly. So how do we, or how can we ensure that the key functionalities that I have described can be aggregated as microservices that are deployed as Docker containers orchestrated by Kubernetes. So these are well-known technologies, and the goal is to bring these microservices together in a way that there is a very seamless and very light end-to-end execution of workloads in these virtual environments, which then means bringing the data to the AI, and at the end of the day, ensuring that some of the data interoperability problems that I've mentioned are being addressed and are being solved actually for the benefit of climate and also for the benefit of everyone. So that's my presentation. Thank you very much. And I think there is like a Q&A opportunity now, Clemens.
Yes, we got lots of Qs. So and you perhaps have the A's for it. No, thanks a lot for the overview. Also to be available at such an ungodly hour at 5:30 in the morning. So let's see which questions we have received. Yeah, good. The first one is quite broad topic, but nevertheless, in the context of your solution, interesting. In which area do you foresee the most successful use cases within the next 5 years?
That's a great question. So actually, I think in renewable, especially in offshore wind, in grid, especially on the DSO level, and on the demand side in VPPs. So these are like 3 hot candidates, and I think that has to do with the economic but also climate improvement potential that we can see in these 3 subcategories. And also, if you look a bit where the AI in energy scene is talking about, then these 3 areas are hot candidates. Yeah?
Great. Then the second one we have is related to security. No, wait. So sorry, our director just cut out the wrong question. Yeah. How do you dispel doubts in the security of using operational data in the rather conservative energy sector?
Yeah, so that is, of course, a challenge. But I have to say that I don't think that the energy sector is really more conservative than some of the other industries. So because of the work in electric vehicles that I'm doing, I have a lot of exposure to the automotive industry, and I don't see really big differences, to be honest. I think you have to have the right concepts. And, you know, I just, because of times, I just could give you a very, very raw idea of how we try to tackle that. But the way it works is that when you have like somebody who has already done it, who comes from an industry like a big energy company. So we have like a bunch of shareholders who are some of the biggest energy companies in the world, and they are working with it, then it's easier to convince others that this is really secure, robust. And but at the end, you have to undergo a due diligence, like a security due diligence. And I think what has changed, and that's my experience 3-4 years ago, it was much harder. I think now people have understood that, you know, there is a sense of urgency, and there are expectations for the energy industry to accelerate the transformation. And then it's really necessary to do something with the data and to do more with the data. So there is movement, but you need to have good answers to the security questions people have.
Great. Yeah. Thanks a lot. And also, if you have anything to share with the audience, when we do a mailing, for example, later on to all participants, just shoot us a link to a white paper or, you know, whatever to stay in touch, or with your contact data, for example. So yeah, thanks a lot for joining virtually. I hope we can grab a coffee next time you're in Vienna.
End of April. I will ping you.
Yeah, perfect. Soon. 10 days to go. Excellent.
Thank you very much for having me. And if there are any questions, I'm very easy reachable via LinkedIn or other means. Thank you so much.
Yeah.
Great being with you, and hope to see you in Vienna next time. Thank you very much. Bye-bye.
Definitely. Bye-bye.
Bye-bye.